This integral is impossible to solve using normal methods. There's no antiderivative, no substitution that works, nothing. But mathematicians found one of the most elegant tricks in all of calculus to crack it. By the end of this video, you'll see why this solution is considered pure genius. We're tackling the Gaussian integral today, the integral of e to the negative x squared from negative infinity to positive infinity. This integral appears everywhere in mathematics, physics, statistics, and engineering. It's the foundation of the normal distribution, the bell curve you've probably seen in probability and statistics. But here's the problem. If you try to find an antiderivative of e to the negative x squared, you'll quickly realize it doesn't exist in terms of elementary functions. No amount of substitution, integration by parts, or clever algebra will give you a simple answer. So how do we solve it? We're going to use a technique so creative, so unexpected, that when you see it, you'll understand why mathematics is truly an art form. Let's define our integral. We'll call it I, so I equals the integral from negative infinity to positive infinity of e to the negative x squared dx. Now, before we dive into the solution, let's understand why this is so hard. If you've taken calculus, you know that to evaluate a definite integral, you typically find the antiderivative first, then apply the fundamental theorem of calculus. But e to the negative x squared has no antiderivative that can be expressed using polynomials, exponentials, logarithms, trig functions, or any combination of these elementary functions. It's just not possible. Mathematicians have proven this rigorously. So we're stuck, right? Not quite. The key insight here is that even though we can't find the antiderivative, we can still find the value of this definite integral using a completely different approach. And that approach involves one of the cleverest tricks you'll ever see. Here's where the genius begins. We have I equals the integral of e to the negative x squared dx. Now watch this. Since we're integrating with respect to x, the choice of variable name doesn't actually matter. We could just as easily write I equals the integral of e to the negative y squared dy, or any other variable. The value is exactly the same because we're just using a dummy variable for integration. This might seem trivial, but it's the key to everything. Now, what if we multiply these two expressions for I together? We get I times I, which is I squared, equals the integral of e to the negative x squared dx times the integral of e to the negative y squared dy. Since these are both definite integrals from negative infinity to positive infinity, and they use different variables, we can combine them into a single double integral. This gives us I squared equals the double integral over the entire xy plane of e to the negative x squared times e to the negative y squared dx dy. Using exponent rules, we can combine this into e to the negative quantity x squared plus y squared. So now we have I squared equals the double integral of e to the negative quantity x squared plus y squared dx dy, where both x and y range from negative infinity to positive infinity. We've transformed our impossible one-dimensional integral into a two-dimensional integral. But why is this helpful? Because now we can use a change of coordinates. Look at the exponent, x squared plus y squared. If you remember your geometry, x squared plus y squared is exactly r squared in polar coordinates, where r is the distance from the origin. This is screaming for us to switch to polar coordinates. Let me remind you how polar coordinates work. Instead of describing a point using x and y, we use r, the distance from the origin, and theta, the angle from the positive x-axis. The conversion formulas are x equals r cosine theta and y equals upper sine theta. And crucially, x squared plus y squared equals r squared. Now, when we change variables in a double integral, we need to account for how area elements transform. The area element dx dy becomes r dr d theta in polar coordinates. That extra factor of r is essential. It comes from the Jacobian of the transformation. So our integral becomes the double integral of e to the negative r squared times r dr d theta. Now here's the beautiful part. We need to figure out the limits of integration. Since we're integrating over the entire xy plane, in polar coordinates that means r goes from 0 to infinity, because r is always non-negative and we want all distances from the origin. And theta goes from 0 to 2 pi because that covers all possible angles, a complete rotation around the origin. This means we can separate our double integral into two single integrals. We get the integral from 0 to 2 pi d, d theta times the integral from 0 to infinity of e to the negative r squared times r dr. Notice these are now completely independent. Let's handle the easy one first. The integral from 0 to 2 pi of d theta is just theta evaluated from 0 to 2 pi, which gives us 2 pi minus 0, which equals 2 pi. Simple enough. Now for the r integral, the integral from 0 to infinity of r times e to the negative r squared dr. This looks complicated, but there's a perfect substitution. Let u equal r squared. Then du equals 2r dr, which means r dr equals 1/2 du. When r equals 0, u equals 0. When r approaches infinity, u also approaches infinity. Substituting, our integral becomes 1/2 times the integral from 0 to infinity of e to the negative u du. And this is a standard exponential integral. The antiderivative of e to the negative u is negative e to the negative u. Evaluating from 0 to infinity, we get negative e to the negative infinity minus negative e to the negative 0. As u approaches infinity, e to the negative u approaches 0, and e to the negative 0 is just 1, so we get 0 minus negative 1, which equals 1. Don't forget the 1/2 in front, so our r integral equals 1/2. Now we multiply our results together. We have 2 pi from the theta integral times 1/2 from the r integral, which gives us pi. So I squared equals pi. Remember, I squared equals pi. To find I, we take the square root of both sides. So I equals the square root of pi. And there it is. The integral from negative infinity to positive infinity of e to the negative x squared dx equals the square root of pi, which is approximately 1.77245. This is the Gaussian integral, and it's one of the most important results in all of mathematics. Think about what we just did. We squared the integral, converted it to polar coordinates, separated it into two simpler integrals, and then took the square root at the end. It's indirect, creative, and absolutely brilliant. Why does this matter? This integral is the foundation of probability theory and statistics. The normal distribution, which describes everything from test scores to measurement errors to natural phenomena, is based on this function. In physics, it appears in quantum mechanics, thermodynamics, and signal processing. In fact, anytime you see a bell curve, this integral is lurking in the background. The Gaussian integral shows us that sometimes the direct path isn't the right path. Sometimes you need to step back, look at the problem from a different angle, and use creativity to find the solution. That's the beauty of mathematics. It rewards clever thinking. If you enjoyed this proof, hit that like button, subscribe for more mind-blowing math content, and drop a comment telling me what integral you want me to tackle next. Thanks for watching, and keep exploring the beauty of mathematics.